Alright, so in our second video on our law of cosines, we're really going to apply it and see how it helps us solve questions. So the first thing that I would look at here is, can I use the law of sines? And I see that it's asking me to determine CB, right? So it really wants me to find this right here. So I have an opposite angle, but I have no other side and angle that I can work with to use the sine law, which means I really need to use the cosine law for this. I have two sides, and I have the angle I'm trying to solve for the side that I'm trying to solve for. So in this case, I'm trying to solve for side A. So I would actually just set up my formula such that I'm solving for A squared. So we had, in the first video, determined kind of how those equations looked. And I have A squared, now remember it's the other two, so B squared plus C squared minus 2BC times the cosine of A. Right, the angle matches up with the side you're trying to find. Now, if I have angle C right here, that means that this is my side C. If I have angle B right here, that means that the opposite is my side B. And that means that my question mark here is really solving for side A, right, opposite the 58. So then I just plug in the numbers that I have for my expression. B squared in this case is 32 meters squared plus C is 40 meters squared minus 2 times B, which is 32 meters, times C, which is 40 meters, times the cosine of 58 degrees. So A squared is equal to 32 squared is 1,024 square meters plus 1,600 square meters minus 2,560 square meters times the cosine of 58 degrees. Which means that A squared is equal to 2,000, if I add together my two numbers, so 2,624 square meters minus 2,560 times the cos of 58. So we can't just subtract 2,560 and then worry about the cosine. You have to do that together in that term. So make sure that you're doing this step as one piece. Okay, so 2,560 times the cosine of 58 gives us 1,356.59 square meters. Because my units are the same, I can combine them together. So in this case, I get 1,267.406 square meters. We'll take the square root of this, so A is going to equal 35.6 meters, and then it wants it to the nearest meter, which means that A is going to equal 36 meters. So using the cosine law, we're just plugging in our values and making sure that when we plug them in, we have the right setup from our triangle that's given. Alright, so we have our next example. I'll get you to pause it, read it out, see if you can figure it out on your own, and then come back when you're ready. Alright, so in this case, diagram on the right shows a plan for a roof. It has the support beam DE, which is parallel to AB. The local building code requires the angle formed at the peak of the roof to fall within a range of 70 to 80. So the angle at the peak of the roof be in here, so that snow and ice won't build up on it. And then basically it says, will this plan, the way that it stands right now, pass code? So we have our triangle set up, and in this case we're actually looking for the angle. So I'm looking for angle B, right? I could find angle E, but I don't know what that length is. But because they're parallel, B and E will be the same because they share corresponding angles. So opposite B, that means that the 20 feet, that's what that little tick is, represents feet, and 2 ticks represent inches. So opposite B means the 20 feet is going to be my side B. Opposite C means the 10 feet will be side C. And then the 19 feet 6 inches, 6 inches is half of a foot because a foot is 12 inches long. So really this is 19.5 feet for my purpose, and opposite, that makes this side A. So I'm looking in this case for the angle B, which means I'm going to solve for B squared. I'm going to solve for that side. So B squared is equal to A squared plus C squared minus 2AC times the cosine of B. And the reason why I picked that formula is because I know that I'm solving for cosine B. So I can actually take this formula and I can rearrange it to have cosine B there. So we can see what that looks like when we're solving for the angle. So the first thing I need to do is I want to make this thing positive. So I'm going to add the 2AC cos B over to the other side. So I'm going to put plus 2AC cosine B on both sides, plus 2AC cos B. That's going to cancel this term out completely, and I'm going to get B squared plus 2AC times the cosine of B is going to equal A squared plus C squared. Okay, all I'm doing is adding it over to the other side. And then in the same breath, I'm going to minus the B squared and put it over to the other side. Okay, so hopefully you can kind of see that part as well, and that gets rid of this. So now my next step is I want to solve for cos B, and this is all being multiplied, so I can just divide by 2AC. Divide by 2AC. 2A and C all cancel out. Cosine of B is equal to A squared plus C squared minus B squared all over 2AC. So now I can see that really I just need to plug in my values into here, and I'm going to have to use the second function button because I'm solving for the angle. So cosine of B is equal to A squared, it's 19.5 squared. Now it's 19.5 feet, and so yes, we will get square feet for all of these. I'm not going to use the tick in there because I just don't want to confuse you with where the numbers are going, because there's no formal letter for the unit. It's just that little mark. So plus C squared is 10 squared, minus B squared, which is 20 squared. That's all going to be over 2 times A, which is our 19.5, and our C in this case, which is 10. So our cosine of B is equal to 380.25. So there's our 19.5 squared plus 100 minus 400 all over 390. So our cosine B value, if I add those up and divide by 390, works out to be 0.2051, which means B is equal to the cosine inverse of 0.2051. So B equals out to be 78.16 degrees. And so will this plan pass the building code? Yes, because it's between 70 and 80 degrees. So yes, it will pass code. Alright, and our next one. A three-pointed star is made up of an equilateral triangle and 3 congruent isosceles triangles, and it wants us to determine the length of each side of the equilateral triangle in this three-pointed star. So the biggest part here, I guess, is it says 3 congruent isosceles triangles. That means that all 3 triangles are the same isosceles triangle, which means that all 3 sides in this equilateral triangle in the middle are going to be the same, which is kind of given the idea that it's an equilateral triangle anyway. So again, it's giving me one triangle to kind of solve for here, and I need to find its missing side. So let's make this C, and then we can make this A and this B, and then it really doesn't matter which one we pick for A and B. It's an isosceles triangle. They're going to share the same angle and the same side. So let's set up our formula. So C squared is equal to A squared plus B squared minus 2AB times the cosine of C. And I have some pretty familiar numbers here because I'm going to have a few duplicates. So 60 squared, 60 centimeters squared plus 60 centimeters squared minus 2, and then 60 centimeters times 60 centimeters times the cosine of 20 degrees. So c squared is equal to, I'll have 60 times 60. So that'll give me 3,600 square centimeters plus another 3,600 square centimeters minus, and then I have 2 times 60 times 60. Well, 60 times 60 is 3,600, and so times that by 2, and I get 7,200 square centimeters times the cosine of 20 degrees. So c squared is equal to 3,600 plus 3,600 is 7,200 square centimeters minus, and then I need to do 7,200 multiplied by that cosine value of 20. And I get 6,765.786. And so I'm going to subtract those. So I get 7,200 minus 6,765.786 square centimeters. And we get 434.213 square centimeters, which means that when I take the square root of that, c is going to equal 20.837 centimeters. And then after that, round the length to the nearest centimeter, which just means that this is going to go to 21 centimeters. So it'll round up. And so the side length of the equilateral triangle, all three side lengths work out to be 21 centimeters. Now with this one, I'll also add in, I guess, that you could probably make this equation a little bit easier in this problem with a little bit of rearranging, although plugging it in this way will work. And the reason why is because this is really specific, because these side lengths are exactly the same. So really you probably noticed a lot throughout here that we had the same number. And in fact, a can just be equal to b here. And you could come up with, I guess, a simpler equation that you could use to work with to solve for side length when you have an isosceles type triangle and you're dealing with that. So I'll just leave it at that because plugging it in here does work and you get the right answer. But you can certainly try something and then check it out and see if you get the same answer, allowing a to equal b, and see if you can make that equation a little bit simpler. So kind of summing some of this up, the cosine law can be used to determine an unknown side length or an angle measure in an acute triangle. And you can see the three formulas are right here that can help us kind of figure these out a little bit better. And so you can use the cosine law to solve problems that can be modeled by acute triangles when either you know two sides and the contained angle. So notice here they know two sides and they know the angle that's between them. Or when you know all three side lengths, because then you can find any angle in there. So that's it for this video. We'll practice a few problems, and if you have any questions, let me know.